Welcome to Lesson 12. So we are going to talk about looking at the relationship between two quantitative variables and interpreting their scatter plots. This should be a throwback to ST201. So when we look at two quantitative variables, we usually designate one as an explanatory variable and one as a response variable. So if one comes first chronologically, just in time, if one is typically recorded first, that is usually going to be our explanatory variable. So the explanatory variable might help or predict the response variable. So knowing what's going on in the explanatory variable might give us information about what's going on with the other. It's our predictor variable. It's the one we're using to make predictions. It's independent variables, implying that it doesn't depend on the other variable necessarily. So x. So this implies it goes on that x-axis. So when you have your axes, your y goes up and down, and your x goes side to side. I know it's cheesy. I like to say my explanatory variable. That helps me remember it goes on the x-axis. The response variable is usually the variable that we're actually interested in making any predictions or estimates about. So it comes from units or people, subjects. It's the variable we usually want to be able to estimate or predict. It's dependent, so the idea is whatever is going on with the response variable is going to depend somewhat on what's going on with the explanatory. And it is the y variable. That means it goes on the y-axis. So for example, we have a problem where a bookstore, they want to use the number of books in a particular order where they're selling orders of books to estimate the shipping weight. So explanatory variable. So here, if you see estimate or predict, the thing that we want to estimate or predict, that's our response variable. So our response variable is going to be that shipping weight. The explanatory is going to be the number of books. So, number of books in order. So the idea here is that we can use how many books are in an order, like an online order, to help predict what the shipping weight is going to be. So here's a scenario that we're going to use throughout the lessons here. We have, and I know it's really, really old school, we have, it's at a particular private college, I believe. They are looking at high school graduate GPAs and comparing it to the GPAs of these students at the end of their first year of college. So they're trying to see, can we predict what the end of their first year college GPA is going to be based on what their graduating GPA was in high school. So explanatory, this is where it comes in handy to know, hey, what order did these happen in? So high school GPA, this happens first, right? Typically, I know that nowadays people can be co-enrolled, but most of the time, if you're attending public education, you go to high school first. Then you go to college. So based on that, we could realistically say we expect that high school GPA is going to help explain that first year college GPA. So once we have scatter plots, we want to be able to describe them. Pretty much true of any kind of plot or graph that we make. So we want to be able to describe things such as direction. So as x is going up, is y going up? Is it going down? Is it positive or negative? That'll really be what it comes down to. Strength is the relationship that we see. Is it weak? Is it strong? Is it somewhere in between? I mean, you can have moderately weak and moderately strong as well. Form, this is going to be less complicated than it sounds. We just want to know, is the relationship shaped like a line or is it not shaped like a line? And then it's usually worth noting outliers as well. So do we have observations that don't fit the pattern? That doesn't mean that you can get rid of them, but it is worth noting them and usually worth investigating them. It's worth finding out, why do I have this oddball data point, and exploring further from there. But you can't get rid of them just because you don't like them. So starting off, we're going to look at direction. So positive versus negative. So positive, so think of it in English, we tend to read from left to right. So as x increases, if the values of y go up. So if I had a little stick figure person and they're walking from left to right, if they're going uphill, that's a positive relationship. Negative relationship, same thing here. Have a stick figure person going from left to right. If they're going downhill, it's a negative relationship. Typically, we're going to, if it's something that's definitely not linear, we may not talk about positive and negative relationships. However, if it is linear, we absolutely will want to know, well, is it a positive linear? Is it negative? Is there just like a zero slope? Is it flat? I mean, it's important to distinguish that. So then for interpreting scatter plot's strength, so we want to talk about how strong that relationship is. So if we see a trend, like a linear or even nonlinear trend, we want to know, hey, do the points, are they really tight fitting to that trend, or are they kind of loose fitting to that trend? So a weak relationship would be like here on this left-hand side. If I were to fit a line here, I mean, the points kind of generally fit that line, but it's not like a pattern jumps out at you and go, oh yes, there's a pattern here. It's not very clear that there's a strong relationship. Which brings us to a strong relationship. If you can say, oh yeah, no, I see a pattern there. Here's a linear pattern. As you know, x increases, so does y. You can see all the points are fairly close to that line. I mean, that's a much stronger relationship. So form. So this is basically saying, is it shaped like a line or is it shaped like anything else? So a linear relationship, it's when it's shaped like a line. Go figure, right? Nonlinear, if it's shaped any other way. If it's shaped like something but it's not a line. So especially curves. Curves are the thing we tend to throw the most at. We usually will have a line or a curve. If you have this right here, it's still a strong relationship. But I would argue, despite it being a strong relationship, it's not a linear one. Okay, and for that last component, outliers. So we want to find points that, given that pattern that the data are following, we want to know, hey, do we have oddballs? So like in this high school and college GPA example, all the points fit this general linear relationship. This one's a little bit odd, given what we see, the relationship between high school and college GPA. That particular student, they had a higher college GPA than we would have expected, given their high school GPA. So they don't fit the pattern. It doesn't mean we get rid of them, but it does mean we usually will investigate. We might look back, see if there are notes in the data, what's going on with this individual. Does this individual belong in the data set? But you have to have a non-statistical reason. So a reason that isn't, I don't like this data point because it messes with things. Reason to remove an outlier. So when we interpret scatter plots, now we want to put it all together. We want to have all four things, and it's also really important to include context. You need to say, okay, there is moderately strong. So looking at this scatter plot, moderately strong, because if we were to fit a line, the points fit the line pretty well. Moderately strong, positive, linear relationship. And then this next part is super important. This is the context. So it's telling us we have this relationship between what? Between high school GPA and first year college GPA. So, and then, I mean, this is just a note here. It appears that students with higher high school GPAs tend to have higher college GPAs, which isn't usually too surprising, to be honest. So, this is us combining all of them. You can mention there's a possible outlier. So there's a student who it looks like they got a 3.3 in high school and a 3.6 at the end of their first year of college, and that college GPA is a little higher than we might expect it to be, given the trend of the rest of the data. So, an example here. So we have a scatter plot. It looks like the jaw width of a shark in inches and the length of a shark. We want to choose the description that best fits these two variables. So I'll give you a moment. It's a great place to pause, and we'll move from there. So for me, one of the first things I like to do is identify, do I see a pattern? And right off the bat, I would say yes. I would see a pattern here. It looks linear to me. It doesn't look curved. And not only that, as X increases, so the length of the shark increases, it looks like the jaw width tends to increase as well. So it looks like I have a positive linear relationship. So I can right away say, okay, well, I can get rid of the nonlinear options, and I can get rid of the negative option. That leaves me with one left. But even if I had narrowed it down to two, this would have helped me a lot. So, and this is a strong relationship. When you look at this particular scatter plot, it definitely looks like a linear relationship. It is a pattern that kind of jumps out at you. You're not looking at it trying to guess what shape it is. It looks pretty linear. Here is another example. So we're looking at the length of an alligator and its weight in pounds. So based on this scatter plot, which description fits best? So like with the last one, I strongly recommend looking at it and saying, okay, is there a pattern that jumps out? Right away, I would say, yeah, it looks, obviously I didn't fit it perfectly. It looks like there's this nice curve shape to it. I would argue that this is nonlinear. So I would argue it's not linear. I would argue, no, there is a relationship. Strong, positive, nonlinear. So you definitely strong and nonlinear, we will want. You could argue it's positive because consistently as X increases, so does Y, so it's appropriate to put here. Although, if we had something more like this, where it's a strong relationship, it would have been totally fine to not say if it was positive or negative, because that wouldn't have been appropriate for that curve. So, C will be the answer here. Just know that if it's nonlinear, it may not always be appropriate to say positive or negative. So here's another. We're looking at average annual Red Sea temperature versus coral growth for 7 years. Once again, draw it out. So when you look at this relationship, when the average sea temperature goes up, it looks like the average coral length is going down. So I would argue it's not a positive relationship. Looking further, I would argue there's a relationship. I would argue this is moderately strong. The points, they fit the line fairly well. When you look at it, you definitely see a linear trend to it. So I would argue the relationship between average sea temperature and average coral growth is moderately strong, negative, and linear. So that's it for lesson 12. I'll catch you for lesson 13.